Hey, good morning. Today is June. I believe it's June 12th, 2026. Today we'll continue the electromagnetism. Again, this is the Gauss law application. Remember before when we calculate the electric field of an infinite large plane with the charge density of the sigma, we try to find the electric field right here, and then we start with the ring, right, and then we integrate the whole disk, and then we let r equal to infinity to get the result for the plane. But today we're going to use a different approach. Again, we have an infinite plane. Let's say the charge density is sigma. Now we are going to draw a Gaussian plane like that. Okay. And then the area of the plane, let's say this is A, this is also A, because this is a cylinder, this is the air, for instance. And then based on the Gaussian law, the electrical flux is equal to E dot A, and then E A cosine theta, where theta is the angle between the electrical field and then the direction of the plane. Okay, so let's first zoom in the middle, for the cylindrical, right? The direction of the area is going to be a radical direction, right? And then the direction of the electrical field is going to be either this way or that way. In other words, the angle between those two is 90 degrees. So if we say phi E middle, which means the cylindrical area, that would be E A, the theta is 90 degrees. So cosine 90 degrees is 0, so the whole thing is 0. Now we only need to consider those two planes. Let's say this is what we call the left plane, and then this is what we call the right plane. Then phi E left, it will be E dot A, and then E A cosine theta. Notice this is the E direction that way, and then the plane of the direction also goes to that way. So their angle is 0, so it will be E A cosine 0 degree will be E A. Now look at the right hand side, the phi E right would be E dot A, and then would be E A cosine theta. Look at this right here. The direction of the electric field goes that direction. The plane direction also goes to that way. It would be E A cosine 0 degree. Again, it would be E A. Based on the Gaussian law, phi E total, which is this side plus the middle plus that side, would be E dot A, and then that would be the total charge enclosed, right? Because that's the Gaussian law. So it would be the Q enclosed divided by the electrical constant. So we know that E dot A is the summation of all these three, which is 0 plus this EA and plus that EA. And then what about the Q enclosed? The Q enclosed is basically, you can view it as the total charge contained in that area. So that would be what? That would be the, because this is the plate, right? We assuming the thickness is 0. So it would be the charge density times the area. That area actually is exactly as this area and in that area as well. So that's A, epsilon 0. So we do a little bit algebraic. That would be 2EA equal to sigma A epsilon 0. We cancel A, we move 2 to here, so we got a E equal to sigma 2 epsilon 0. Okay. So the next thing I want to share with you is, what if we have two conduction plates? One is positive charge, another one would be negative charge. See, when you look at the problem, you have to pay attention to the keyword called conducting plate. Since the both plates are conducting, so the charge, once they had a different polarity of the charge, they're going to attract each other. Why? Because the charge can freely moving between the plate, right? So in other words, if we draw a Gaussian plane, let's draw it right here. If we draw Gaussian plane like that, notice inside right here, it doesn't contain any charge at all. So this part where the E dot A equal to Q enclosed epsilon 0, so the Q enclosed is 0, right? So if this is 0, A is finite, then E is equal to 0. Similar right here. But what if I draw a Gaussian plane like that? Okay. So that including the positive charge like that. And then they also have a area is A. Then we know for this side, it doesn't including any electric field at all, because the electric field is going that direction, right? So, and then from this problem, we know the angle between the area and the electric field is 90 degrees. So that also gives us the electric flux is 0. So the only thing I have is this part right here. So that would be phi E would be E dot A, and then that would be E A cosine theta, and then the direction of the area is that, and the electric field is also in that direction. So it's E A cosine 0 degree. So cosine 0 degree equal to 1, so that would be EA, right? And then according to the Gaussian's law, the phi E equal to E dot A, and then also equal to Q enclosed over epsilon 0. In this case, the Q enclosed will be this Q right here, which is Q enclosed would be, let me see, it's charge density times area, right? So that's that part, epsilon 0 is right here. And then here what we have is just E dot A, right? Because the angle is actually EA, okay? And then A cancel out, so this E equal to sigma over epsilon 0. So those two are exactly the same as what we did from the previous lecture. If you forgot, I suggest you to go ahead, check the previous video. You will know what I'm talking about. Again, those two results, the first result, the second result, are very important. This one is for the infinite large plane, and any distance away from that is have nothing to do with the distance. If it's outside of the plane, that is the sigma over 2 epsilon 0. However, if we have two parallel planes, we want to find the E between 0. Instead of 2 epsilon, it's just epsilon. The rest is the same. So I want you to memorize those two formula or equation or whatever you call it. This is very, very useful in our calculations. And then next lecture, I think I'll probably just move to the next subject instead of talking about Gaussian's law. Even though there's a lot of problem about Gaussian's law, I try not to continue to do that because you guys might get bored pretty soon. So I want to try some new topics. But if you have any questions regarding this, or if you want me to discuss more about the Gaussian's law, please leave it in the comments so that way I know exactly what you guys need. With that being said, thank you again, and I will see you next time.